Okay, so 2 weeks ago we looked at the factors that affect the value of an option, right? So, and then we look at, we use those same variables to price an option using the binomial model last week. And we're going to use these same variables in the Black-Scholes model again this week. Okay, now last week when we looked at the binomial model, we made use of decision trees to determine the value of an option, and we do that by working backwards from expiration date, right? Can someone remind me why do we start with the expiration date when we value an option? So with the decision trees, we determine the value of an option at expiration, and then we work backwards to whichever period we want, right? So why do we start with expiration date? Anyone? How about you? Why do we? Okay, how do you calculate the value of an option? Do you start at expiration date or do you start now? Expiration date, right? Can someone remind me why do we have to start at expiration date? So therefore, it can be determined with certainty, right? There's no ambiguity with that. It's either 0 or something, right? Now last week also we looked at hedging a portfolio, right? Such that if it's properly hedged, then we earn the risk-free rate of return. Yeah, and in doing so, we need to calculate the hedge ratio. Now, I hope you remember that concept. It's a very important concept, delta hedging, and we will be making use of the concept again in today's lecture to see how the Black-Scholes model is developed. Okay. Now, the binomial model, as we said last week, look at time from a discrete perspective, right? So time lives from today to tomorrow and nothing in between. Now, the Black-Scholes model operates from the opposite spectrum of time, so it is continuous. So it doesn't live from today to tomorrow, it goes continuously. Okay, so in other words, the value can therefore change any time. Yeah. So in looking at the Black-Scholes model, I will look at a partial derivation. Okay. Sorry to disappoint you if you like the maths. So we look at a partial derivation. Partial derivation because I have basically picked stages of the derivation that I think is important for you to appreciate the theory behind the Black-Scholes model and to understand how the Black-Scholes model comes about. Now, a full derivation is not required in this course, but if you are really interested in the maths, there's a course called financial modeling that you can take. Okay, so and the differential calculation itself, the differential equation itself is not used in the application. Okay. In fact, that's just to show you how the Black-Scholes model was developed, and the Black-Scholes model itself, which is going to be used in your calculation, is not in the form of the differential formula. Okay, so you won't be asked to derive the formula. Okay, so rest assured, just focus on understanding the theory and know how to apply the actual formula itself. Okay. Now, as we know, options derive its value from the underlying, right? Now, in which case it's a stock for us, because we're looking at stock options. So in order to understand how options work, you first have to understand how the price of the underlying behaves, in this case a stock. So we'll start off with looking at how stock price behave, and then move on to the Black-Scholes formula, and then we'll do some numerical example. Is there any question from last week? No? All good? Okay, so to model stock price behavior, we use what is called a stochastic process. Now, what is a stochastic process? Well, to put it simply, a stochastic process is any process that has a randomness in it. Okay? So it has an uncertainty. So therefore, if you look at, let's say, probability theory, it is simply a process that involves chance. Okay, it generally would refer to a family of random variables indexed against some other. So the stochastic process seeks to describe the change in the value of the variable over time. Okay, the probabilistic change in the value over time. So a stochastic process usually have a deterministic component, but not necessarily so, but it must have a random or an error term. Okay, so you can think of many examples that is in fact a stochastic process. Your time series, for example, is a stochastic process. Your Poisson distribution is a stochastic process. Indeed, life is a stochastic process, right? Because so many things in life are not a certainty, right? There's a random element involved. Now, stock prices also have been shown to follow a Markov process and also to exhibit the properties of a weak form market efficient. Now, what is weak form market efficient? Well, your friends here said that whoever comes in last will have to answer the question. So, well, what do you think? What is a weak form market efficient? What do you think is a weak form market efficient?
When we public information
Okay, so what does that mean? Is past or historical prices relevant or not?
We can't use those past information.
So you can't use historical values, right? You can't use past prices
to predict some
okay.
price in the
Okay,
future.
very good. So you can't use the past to predict the future, right? So what I have here, this formula here is both a Markov process as well as a stochastic process that exhibits the properties of a weak form market efficiency. Now, Markov process looks at a series of random events and attempts to analyze the probability of one event to be followed by another. So this stochastic process here, as you can see, has a random term. So it qualifies as a Markov process. It is also weak form market efficient. So it's a particular type of stochastic process whereby only the current value of a variable is relevant to predicting its future. Now, can you see from the formula whether or not there is a historical component in there? Do we use past prices? What do you think?
T minus 1 is the past.
So you think T minus 1 is historical? Okay, so I have Pt equals Pt minus 1 plus an error term, right? Plus randomness. Now, is this historical or not? Why do you think it's historical? Because it's T minus 1. Okay. I have a question like this in an exam a while back, and some students got it wrong, which I was quite surprised. Because it's a simple question, you should all get it right. So the way to look at this is that what are you trying to predict? Which period are you trying to predict? T, right? So if T is the future, where is the current? It must be T minus 1, right? So I can write anything here, it doesn't matter. You have to look at it in terms of which is the period you're predicting, and therefore the period before that must be the present, right? And the period before the present, then is the historical, right? Okay, so if I give you another example, say Pt equals to, so this is weak form market efficient, right? Because we're not using historical prices. If I have PT minus 2 plus PT minus 1 plus E, is this now weak form efficient? Where is the future? PT, right? Where is the current? T minus 1. So do we have a historical price here? Yes, right? T minus 2. So this is no longer weak form market efficient. Okay? So this formula, if I had written this one, right? If I had written PT plus 1 equals PT, would you have guessed it correctly then? Well, compared to this one. Let's say I didn't give you this one earlier on. I give you only this. Would you say this is weak form market efficient or not? This is not. This is not weak form market efficient. Okay, you told me earlier on that this is not, right? Because T minus 1 is history, right? So ignore this. If I give you this, what is T? T is current, right? If by your argument T minus 1 is history, T must be current, right? Okay? So it can be very confusing if you think in terms of T as the current, and therefore T plus something is the future, T minus something is history. Okay, so stop thinking that way. Instead, think about what you're trying to forecast, the left-hand side. What is this? So therefore, what is the period before this? Okay?
Will it become a strong market efficiency?
We're not considering that because as far as our study with stock price is concerned, we're only interested in whether or not it's weak form, right? So if I give you, let's say, one more example, PT minus 3. Let's say this is PT minus 5 plus PT minus 4. Is this weak form market efficient? Yes or no? They are all historical prices. Are they? Are they all historical prices? They're not, right? Because we're trying to predict PT minus 3. So is this weak form market efficient or not? Yes or no? No, why is it not? What do you think? You're very focused. What do you think? Is this weak form market efficient or not? It's not all historical price. That's why I told you you have to stop thinking that T plus something is future, T minus something is history. You have to always look at this term here, the term that you're trying to predict. So whatever this is, one period before this must be the current, right? If this is the future, one period before this must be the present, right? So what is one period before this? T minus 4, right? So if I don't have T minus 5, then this is weak form market efficient, right? But because I have T minus 5, then I'm using historical. If this is future, this is present, this must be historical, right? So it's important to realize that because I can write it any which way I like. And although you might think that T minus something is historical, well, yes, maybe it is, but that's not the point. The point is what are you trying to predict, right? So if you come out and work and your manager tells you to do some back testing, right? To see whether a formula or a certain model that you want to use to price stocks is correct or not, then you're going to have to use historical prices, right? So let's say I use last month's prices to test my model, and in testing my model, I want to predict using historical prices whether the prices last week is going to be based on something before that or not, right? So last week therefore becomes my future, so to speak. Do you follow me? Okay, so it's important that you be able to distinguish that. Okay, a binomial model, as we said last week, is a discrete time model. Now, is a binomial model a stochastic process? A stochastic process is one that involves uncertainty, right? That involves randomness. So is a binomial model a stochastic process? Why do you think it's not a stochastic process?
The probability is certainty.
Where is the certainty? It can either go up or go down, right? And it can go up first and continue to go up, or it can go up first and then come down, or it can go down first and then go up, right? So there are many possibilities, right? Yeah? So there's uncertainty, right? So therefore, a binomial model, notwithstanding that we call it a discrete model, is also a stochastic process. Okay? Now, it is a discrete model only with respect to certain things. It is a discrete model with respect to time, as we discussed last week, because time moves from today to tomorrow, right? And nothing in between. So in other words, a binomial model is discrete because price can only change at specific intervals of time. Okay, today and tomorrow, nothing in between. Okay, it's also discrete with respect to values. In other words, the price at 100 today can go up to 110 or 90 or go down to 90 and nothing in between. Okay? So it's discrete with respect to time and value such that it can only change at specific intervals of time. It can only take certain values. Okay? It will from 100 go to 110 and not 101, 102 and all of that. Okay? Now a continuous model such as the Black-Scholes looks at time from a continuous perspective, and therefore the value can change anytime. From today to tomorrow, it can change anytime. It doesn't change from today and jump to tomorrow. Okay? And it's also continuous with respect to values. So therefore, it can take any values within a specified range. Is the distinction clear to everyone? Yes? Okay, I see some heads nodding, so that's good. Okay, so next we look at what is called a Wiener process or a Brownian motion. Now, Brownian motion is not a new concept. Okay? Are you familiar with Brownian motion? A little bit. You study physics. Okay, very good. So what applications do you use in physics? Okay, so in physics you could use Brownian motion to look at the diffusion of particles when subjected to large molecular shock, for example, right? So that's something you studied in high school. However, it is used across many different disciplines. Okay, so for example, in applied maths, do you use that in applied maths?
No, I didn't study physics.
Oh, you don't even study physics in high school? Okay. So what do you study? Biology.
Bachelor degree, I study political science.
Okay, so it's used in many applications. For example, in applied maths, it is used in the study of continuous time martingales, for which more complex stochastic process can be described. Pure maths too uses Brownian motion to basically represent the integral of Gaussian white noise. And I don't know some of you whether anybody did engineering or is doing engineering. In engineering especially, there is wide usage of this as well. So for example, it is used as a model for instrument error in filtering theory. Is used as a model for unknown forces in control theory, and so on and so forth. So what we're going to use, what we're going to try to do today is to make use of Brownian motion to explain phenomena in finance. Okay, for example, we can use that to look at how a basket of stocks, such as an index, behave when, let's say, subjected to news, because when you know that when a piece of news hits the market, certain stocks will go up, certain stocks will go down, right? Depending on its impact on the stocks. What example shall we use? So I'm going to show that prices can disperse when a piece of news hits the market, let's say. Okay. How many of you play pool or snooker? Do you know what is pool or snooker? Okay, it's a table like this, right? And it has, you put your balls here, and then you use a cue to, okay? So let's say, come on, I'm sure some of you play that, right? No? The guys? Nobody play pool or snooker? You do? The other way around. Okay, it shows that I don't play. Okay. So what do you play, snooker or pool? Pool. Okay, let's play snooker. Do you play snooker? About the same. I thought snooker is more challenging.
It's the point system.
Okay, you have is it yellow ball? Yellow ball, green ball, brown ball, blue ball. No, blue ball is here, right? Pink ball, black ball, right? And you have your cue. You have your white ball. Where do you put your white ball? How good are you at this? Can you? No. Can you be certain that when you hit the, let's say all these red balls here, all the red balls here, if you hit the red balls here, you're certain that this one would go inside here, and this one would go inside here, and maybe this one would go inside here, and maybe this one would hit here and go inside this pocket. In one cue. Can you do that? Where do you put your white ball? Where do you normally put the white ball? So you play. I see. Okay, let's say you put your white ball here, okay, and your cue here. So let's say your piece of chalk is here, okay. So after polishing your cue and you take in, your white ball hits, let's say, here, okay. So what happens? These balls disperse, right? Yeah. So you imagine this, all these red balls here to be an index of stocks, okay? And the white ball is the news. So when the news hits the market, the red balls disperse, right? And in the same token, what it means is that the impact on the basket of stocks is different for every stock. Some would go up, some would go down, some would go up by a lot, some would go down by a little, right? So what it means here is that you can actually, well, you can't tell for certain what is the effect on each of these stock, right? Just like you can't tell whether it's going to go in here or go in here or whatever. But what you can tell for certainty is that let's say this is time, okay? Now, given more time, it will move by a longer distance, right? Yeah? So given more time, the stocks disperse further, and therefore it achieves a longer distance, just like the stock prices. And we can measure this, right? Because this is the dispersion, right? They spread out. So you can measure this dispersion. And what is this dispersion given by? This is sigma squared, right? And because of the time factor, it must be sigma squared time, right? Now, what is risk in, what is the measure of risk in finance? Standard deviation, right? So therefore, if you want to take the standard deviation, then you take this whole term, then you take the square root of this whole term, right? So sigma squared t now becomes sigma square root t. Yeah? Does everyone follow? Okay? So Wiener process is basically an extension of the Markov process for which the drift rate is equals to 0 and the variance rate is equals to 1. Now, drift rate measures the mean change in the value of a variable over time. So a drift rate of 0 means that the expected value of z in the future is going to be the same as it is today. Okay? So the key is the drift rate, and what do you have in your slide? Is this A or sigma? Is this A or mu? And this is B, not sigma. Okay, can we change that to mu and sigma? Okay, so the key is the drift rate given by mu, which is the return of the stock over time, and sigma, which is the volatility. Okay, now key to understanding Wiener process is this dz here. So dz here is the randomness. Okay, it measures the randomness. So in other words, it is what is normally called noise in the market. Okay, it is the variability of the path taken by x. So it's the noise in the market. So if it's a noise in the market, you don't know what it is, right? So so it can be a random value. So let's have a stock price. So the change in the stock price must be equals to the stock price today minus the stock price yesterday, right? Now if you rewrite that in calculus form, then you're saying that ds equals to mu dt plus sigma dz. Okay? Now remember the key to this is the dz, okay, which we are trying to eliminate in the BlackScholes formula. So if you allow dz to be epsilon square root t, such that epsilon is the random term or the error term that follows a normal distribution of mean, because it's a normal distribution, so it's mean 0 and standard deviation of 1, right? Remember your statistics? Okay, so if you allow dz to be epsilon square root t, then you can rewrite this formula here as mu dt plus epsilon square root t. So you simply replace dz with epsilon square root t. Okay. Now, if you recall last week's lecture when we talked about the formula for u, what is the formula for u? What do you think? Don't remember already. Okay, u is equals to e to the power of sigma square root t, right? So I've just explained to you why is sigma square root t, and why do we use e? Because stock price is not normal, right? It's not. It doesn't behave in a normal, according to a normal distribution, unless it's very short term. So the price of a stock is equals to mu dt plus sigma square root t, right? So drift, this is the drift, and this is the volatility. Sigma is the volatility, mu is the drift. So the key to understanding how stock price move is in the drift and the variance or the volatility. So the drift basically measures the direction or the trend of the stock. So if the drift rate is positive, it means the stock is trending up. If it's negative, then it's trending down. Of course, if it's zero, then it's flat, right? Now the volatility represented by sigma measures the wave. Okay, so if sigma is big, then you have a big wave. If sigma is small, then you have a small wave. Okay, now if you combine the two, this is what you get. And if you look at charts, some of you who trades in the market and technical traders, you probably look at a lot of charts, right? So this chart here is the result of combining that two together. Okay. So you've got a stock worth $100 that pays no dividend. Volatility is 30%, expected return is 15%. So you know the formula from your preceding slide is mu dt plus sigma dz, right? So therefore mu is 15%, 30% for your sigma. You have 0.15 and 0.3 here. What is time? this is 1 week, right? So how do you get 0.0192? 7/365? I told you last week that if you are given time in terms of days, then the denominator is 365, right? But if you are given in terms of weeks, then the denominator is the number of weeks in the year, right? So it's 1/52. Well, that's a slight difference, right? Okay, so that's how you would want to use it. So 1/52 gives you this, and therefore you plug it into the formula. So you are telling people that your model says the stock price would increase by roughly 0.3% plus minus 4% because of the epsilon, the random term, right? So if you say that stock price is going to go up by 0.3% plus minus 4%, how confident are you? What do you think? If you tell someone this and someone asks you how confident are you, what are you going to say? What percentage confidence? 95%? Why 95%? No, it's stated there. But you need to fall back on your statistics. So it has a mean normal distribution, right? So mean zero standard deviation of 1, right? So with a standard deviation of 1, what is the confidence? Forgot already. So it's roughly 70%, right? Yes? Remember? Yes or no? Yes or no? Oh, forgotten. Okay, so it's roughly 70%, right? 60 something, close to 70%. So you can therefore make a statement like this with roughly 70% confidence. Okay? Have I lost you somewhere or not? Are you okay? With the confidence, is it? So if it follows a normal distribution, okay, epsilon follows a normal distribution. Epsilon is a randomness, right? If it follows a normal distribution, under the properties of a normal distribution, the mean is 0, right? And the standard deviation is 1, right? And if the standard deviation is 1, what is the confidence interval? Remember, your confidence interval is always 99, 95, or close to 70, right? So at a standard deviation of 1, your confidence interval is roughly 70%, right? Okay. Okay, next we look at returns. Now, what kind of returns should you be looking at when you are invested in the stock market? Should you be looking at simple returns or what form of return? Now, it's very important to understand this, especially if you are investing. So let's say you start off with 10, okay, 10 million, let's say, and in T1, this goes up to 20. So how much have you made? How much have you made? In percentage, how much have you made? 100%? So in T2, let's say you're back to 10. How much have you lost? 50%. So you're actually still up by 50%, right? But it's not true, right? Because you're back to status quo. Okay? What about let's say t is equals to 10 and t1 you are now at 5. How much have you lost? 50%. So in T2, if you make 50%, you should then break even, right? Yes. Okay, let's see. I hear a yes. So if you make 50%, what is 50% of 5? 2.5. So what do you have here? 7.5, right? And you break even, right, in percentage terms. But you actually lost money, right? Yes or no? Yeah. So it's very important that if you're invested in the market, you understand how returns are calculated. Okay, because I could tell you that, look, you broke even, but in reality you don't. Okay? So prices tend to be log normal. As a result of that, you need to calculate your returns in terms of the natural log and not simple returns. Okay? Now, if you look at a log normal distribution, it's skewed to the right. Yeah? So what does right skew means? So stock prices over the long term tends to skew to the right. What does that mean? So what is the implication? The implication is that there is a greater likelihood of a larger than normal return in the long run, right? Okay? Which is why you always hear people say that, you know, you can't go wrong investing in equity because so you should start investing in equity when you're young because in the long term you will always make money, right? Now, so in the short term, very short term, it would be like a normal distribution, but in the long term, it will then become log normal with a right skew. So therefore, you should always calculate your return in terms of the natural log and not simple returns. Okay? Now, if you look at the next graph, I have a curvature here. So what does that mean? Does it mean that if you invested in stock here, then you're going to not do so well, but if you wait until a later point in time, then you're going to do better? Does it mean that? What do you think it behaves as a curvature? It is not that, right? It is simply due to the effects of compounding. Okay? So we're going to look at two types of volatility. We're going to look at historical volatility and we're going to look at implied volatility. So we will look at implied volatility next week, and this week we'll see how we can calculate historical volatility. Now, if you start off with, let's say, daily prices, okay? So you have all your prices for the day, right? To calculate historical volatility. So what is the next thing you need to do? You need to calculate the return, right? And what is the return for the day? It becomes what? PT minus 1? Divide by? Divide by what? We just talked about it, right? What return will you use? Not simple return, right? We have to use the natural log, right? So it becomes the natural log, right? And then so you have your daily returns. Now if you use any spreadsheet, you would then be able to calculate your volatility, right? Your standard deviation. Okay? So what is this standard deviation? This is equals to sigma what? Day, right? Agree? Because you're using daily prices. Okay? Now what should you be looking at? Annual volatility, right? Just like your interest rate is given as an annual number. So how do you convert this to annual volatility? Times what? So this is another common error among students because they stop right here. Okay, so you have to convert to annual. So how do you do that? You remember this formula? Okay, so you have to times by something, right? And what is this equals to? How many days? Why 260? Yeah, but last week we said divide by 365, right? Because last week we talked about options. In this example, it's about stock. Right? So therefore you take 260. Okay? So you have to be careful what underlying instrument it is. Okay? So if this is bonds, for example, then you might use 360. Okay, and not 365 or 260. Okay? So it depends on what. Now if you want to calculate this instead of daily prices, you have, let's say, weekly prices. So therefore this becomes week, right? So to get annual, what is this number going to be? Then it becomes the number of weeks. Okay? So these are little things that you have to be very careful in order that you don't make mistakes in your calculations. Okay, so using stochastic calculus, so the change in a call is given by this. Now, if you were to measure the change in a call at any point in time, what is how does the graph of a call looks like? You know it's going to be a curve, right? Before it collapses into its intrinsic value at expiration, right? So if this is a curve, if we were to measure the change, let's say this one, this is not going to be very accurate, right? Neither is this going to be very accurate, right? So to get to the accuracy level that you want, you're going to have to measure the change of the change, okay, many times over. Okay? So you're going to have to measure the change of the change, and this leads you to what is called the Taylor series. Okay? So we'll stop. The Taylor series effectively goes to infinity, but we'll stop at the second order. Okay? So making use of the Taylor series and making use of Itolemma, we can then determine the value of a call. So what is Itolemma? Well, Itolemma is simply the method to calculate the differential of a function of a stochastic process, okay, using Taylor series. Okay, so you can see that this is the Taylor series up to the second order, right, from the preceding slide. Okay, so in the preceding slide, we look at the change in a call as a function of time. Okay, now we look at the change of a call as a function of both a stock and a time. So this is the stock element. Okay, this is the time. Can you see that? Now you would also notice that we basically use almost all the variables that we talked about that will affect the value of a call, right? We have stock, we have volatility, we have everything. So this is Ito's lemma. So the idea is very simple. The option price and the stock price depend on the same underlying source of uncertainty. So the stock has an uncertainty in dz. Okay? The option, because it derives this value from the stock, also has an uncertainty dz. So they both have the same uncertainty. So therefore, if we were to create a portfolio consisting of the stock and the option, we can then eliminate the uncertainty. Okay, so in other words, so you remember that the value of your portfolio from last week is HS minus C, right? And this is your H ratio. In other words, how many stocks you hold for every call you short, right? Now, if this is risk-free, then this must be equals to interest rate, right? So how do you get this to be risk-free? Well, two things are very important. One is the H ratio has to be correct. The other one is the direction has to be correct. So by direction, I meant if you were to short the call, do you long the stock or do you short the stock? If you were to long a put, do you then long a stock or do you short the stock? We discussed that last week, right? So that is the direction. So if you get that direction correct, then the risk of the stock and the risk of the option compensates. But it won't compensate completely, right? It will compensate. Now, you can imagine, therefore, that if you get the direction wrong, then it won't compensate, right? It will increase the risk, right? So you have to get it right so that they compensate. But they won't compensate completely unless you get the H ratio correct. Okay, so two things are important. You have to get the direction correct, you have to get the H ratio correct. Once both are in place, then you will earn the risk-free rate of return because the risk is then completely eliminated. Okay, so that's the basic idea within the Black-Scholes model. So in the preceding slides, we have the formula for a stock, mu ds plus sigma dt, right? Okay, in the preceding slide, we saw this formula for a stock, and in this formula, we saw the formula for a call. Okay, now both of them has the random term here called dz or delta z. Okay, so we're going to eliminate this. Once we eliminate this, then it becomes riskless, right? So how do we do that? Well, we know that for every call you short, you would long H number of shares, right? So that's called delta H. Now, in the Black-Scholes formula, we don't call that by the small letter H, we call it by dc over ds. Now, to help you understand why it's dc over ds, what is the formula for H? For the H ratio last week? H is equals to, just intuitively, what is H? Just describe in your words, in your own words. What is H?
If you buy one option, if you share one option, you need to buy how many share to.
Yeah. So what is the H ratio? How do you determine the H ratio? The H ratio is essentially the change in the option over the change in the stock, right? What is your formula? H is equals to Cu minus Cd over Su minus Sd, right? So it's the change in the option over the change in the stock. So therefore, it is in calculus, written in calculus form, is dc over ds. Okay? So if you create a portfolio like this, short a call, long dc over ds shares, then you must put a minus sign here, right? Because you short the call. Okay? Do you follow or not? Okay, so you put a minus sign here. So all these terms become minus, right? Agree? If you put a minus sign here, everything on the right hand side becomes minus as well, right? And because you long dc over ds shares, then you must times dc over ds here, and therefore everything here is multiplied by dc over ds. Do you follow? Okay, I'll write it down for you. I'll just copy down the formula and then you see US Okay, these are the two formulas, right, on your slides. Okay? So if you short a call, then you put a minus sign here, right? So all of this becomes minus, right? Minus, 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 minus. Agree? Yes? So if you long DC over DS shares, then all of this becomes DC over DS, DC over DS. Agree? Yeah? Now, if your portfolio comprises of this plus this, then this cancels this. Right? Okay? And what else? What else cancels? Anything else? Will this cancel? This cancels, right? So you're basically left with this term here, right? Agree? So you find that when you create a portfolio using the H ratio, and if the direction is correct, then you basically can eliminate the randomness in your stock as well as in your call. Is that clear to everyone? Are you good at that? Yes? Okay. So as a result, the uncertainty has been eliminated. Okay, so the value of your portfolio is given by this short a call plus long DC DS stocks. Now, if you measure it over time, then it becomes the change in your call and the change in the value of your stock, right? So if you substitute that, so the dz has gone. So the resultant term, as I draw for you there, there's only two terms left, right? So if you substitute that, you find that this becomes the Black-Scholes differential equation, okay, which is dc over dt, which is basically the call plus the stock, okay, and it's equals to the risk-free rate of return. Now, if you look at the differential equation, have we accounted for all the variables that we talked about? Yes or no? Is there anything missing? So we have time, we have stock, we have volatility, we have interest rates. Did we miss out anything? So did we miss out anything? There is no strike price in there, right? Why isn't there a strike price inside there? Well, because the strike price is fixed, right? Okay, so it's like the boundary, okay? So when time is at expiration, it is simply s minus x, and if it is before expiration, then it's simply the present value of x, because you don't pay out x in the present moment, so you account for the present value of x, okay? Okay, assumptions. So you know that stock price behave randomly, right? It's largely unpredictable, and it follows a log normal distribution as we discussed. So that implies that there's a right skew to your returns. And under the Black-Scholes model, it also assumes that R and sigma are constant. Now, you know sigma is not constant, right, in reality, so the assumption that sigma or volatility is constant is almost always not true. Now, as to interest rate being constant, it is to a lesser extent more true, right? Because when will interest rate change? They don't change every day, right? So they may change after a month, or they may change after a quarter, or they may not change at all, depending on how often central banks meet, right? Some central banks meet quarterly, some meet monthly, so that's as soon as any interest rates can change. And even if they do change, they're not going to change by a lot, right? You don't expect interest rate to be 5% today and 10% next month, right? So the changes will be very small. So the implication or the effect of the assumption that interest rate is a constant is not very significant, okay? No taxes, no transaction costs. You know that's not true in the real world, but we can relax that assumption. No dividends paid, that can be true, that can be not true also, depending on what stock you look at, right? Because some stocks pay a dividend, some don't. However, that's not an issue here because we know how to account for dividends if the stock pays a dividend, right? It's more suited for European options, primarily because the Black-Scholes model is not as flexible as the binomial model to account for the early exercise of an American option. Because with the binomial, you can tell at every node that you determine whether or not the American option is worth more than the European option or not, right? And how do you determine that? So we say that the value of option is basically the discounted expected value, right? Discounted to the present. Now with American option, it is not necessarily so, right? What is the value of American option? So European option is the greater of 0 or the discounted expected value. What is American option? The greater of discounted expected value and what? 0? Last week. Half correct, not underlying value. You only got half of it. So you want to say something? Okay, with American options, because you can exercise, and once you exercise, what do you get? Intrinsic value, right? So then it becomes the greater of the intrinsic value or the discounted expected value, right? Whereas with European options, you can't exercise, and therefore at any time prior to expiration, it is simply 0 or the discounted expected value, right? And we found that we could actually determine that quite easily with the binomial model. However, the Black-Scholes model is less adept at that, okay? So continuous time, we talk about what is continuous time. Risk neutral pricing, we talked about that last week. Okay, so now we're moving into the Black-Scholes formula proper. Okay, so ND1, ND2 is the cumulative normal probability. Always remember your sigma and your R has to be an annual rate, right? So when it's given to you, it's always an annual rate, so you have to account for the time period that you want to use it. So here is the Black-Scholes formula. A call is equals to SND1 minus the present value of X times ND2, where D1 and D2 are given by these two formulas here. What is the formula for binomial? Can someone remind me? What is the formula for binomial, for a call? P plus and okay, do you know why you have difficulty recalling? In general, right? Not just you. Because you have not trained yourself to think in the manner that you're supposed to be thinking. You only need to remember one thing. It is the discounted expected value, right? So if it's a discounted expected value, what does the denominator has to be? It must be your interest rate, right? Okay? So if you think like that, there's less things for you to remember because you just think through the process. Okay, and that's how I want you to learn the course. Because it will stay with you forever, right? Otherwise, after the exam, you forget everything. But when you come out to work, 10 years down the road, you still remember because your foundation is strong, right? Okay, so C is equals to S ND1 minus present value of X ND2. So what does that mean? Essentially, this means that the value of a call is simply equals to stock minus present value of X, right? Plus what? ND1, ND2. Plus the probability of your call being in the money, right? Because if your call is out of money, it's zero, it's worthless, right? So this means S minus present value plus the probability of your call being in the money, okay? Now if you look at D1, D2, it also has all the variables that we talk about. And it's important for you to understand that D1 increases as most of your variables increases, okay? So again, that is something that you want to develop intuitively. So we'll talk about that in what I call a robustness test shortly after this numerical example. So you have interest rate, you have all your strike prices. So in summary, your stock is $8, strike price is $7.75, interest rate, volatility, and so on and so forth. So first you have to compute your D1 and D2 and then find the probability and then stick it into your formula. So what is D1? Log S over X, right? So log S over X plus R plus sigma squared divide by 2 times time, right? Divide by sigma square root time, okay? So it gives you your D1. Your D2 is, what is your D2? D1 minus D1, right? D1 minus sigma square root T. Okay, so it gives you your D2. Look up your ND1, ND2 in the probability distribution table which will be given to you. You find that ND1 is 73, ND2 is 72. So you plug this into your formula, you have your call equals to S ND1 minus X ND2, okay? And this is your present value, okay? So it gives you the value of a call to be 32 cents. Now, is this value correct or not? 32 cents. Well, it's mostly correct, but there are certain factors that can throw this off by a little bit. So this is a good time for you to look at one of the articles I put up on my uni called What Could Go Wrong with Option Prices. Okay? So there's an article that I put up there. Look that up. It's a good time at this stage for you to read that because you will understand better. Okay? If in week 1 you attempt to read that article, you probably don't mean anything to you. Okay? So to recap, option pricing is essentially based on arbitrage. It uses risk-neutral pricing and is nothing but the expected discounted payoff, right? And you're only interested if S greater than X in the case of a call because out-of-money calls are all worthless, right? Okay, so next few slides, we're going to look at how Black-Scholes model behave in different scenarios, okay? So first we look at a stock. Now always fall back to these 3 formula in your Black-Scholes, okay? So a stock price increase, what happens to your D1 and D2? Again, this is something I want you to try and think by looking at a formula, okay? Then it will become very intuitive to you. So a stock price increase, now you look at your formula. So as S becomes very large, so this numerator becomes very big, right? What happens to D1? It approaches 1, right? Okay? And D2 would also approach 1 at the limit because it's D1 minus sigma square root T. Okay? So at the limit, D1 and D2 approaches 1, and therefore your probability also approaches 1, right? So if your probability is 1, ND1 and ND2 is 1, then the value of your call is simply s times 1 minus present value of x times 1. So it's simply s minus present value of x. Is that clear to all? Yes? All good? Now as x becomes very small, what happens? This number becomes very small, right? And therefore, if it gets close to 0, it becomes negligible, and at the limit, d1 and d2 approaches 0. And if d1 and d2 approaches 0, and d1 and d2 equals to 0, and therefore your call is 0, because s times 0 minus x times 0 is 0, right? And that happens when your call is out of the money, right? Because as s goes down, such that it goes below the value of your strike price, then your call is out of the money, right? So therefore it's 0. Okay? So I hope you see this. Before this lecture, we talked about a call is worthless, is equals to 0 if s is less than x, right? So that is the intuition, okay? Because when you exercise, you pay x and you receive x, right? So if s is less than x, then it's worthless to you, right? So first we look at developing that intuition, and now we look at it mathematically to show you that this is indeed the case. Okay? So what happens when time is equals to 0? When is time equals to 0? At expiration, right? So when time is equals to 0, what happens to d1 and d2? Well, substitute time with 0, time with 0. So if this term becomes 0, this is 0, and if your stock is greater than your strike price, then you have a positive number here divided by 0, right? If you don't follow, please shout out, okay? Do you follow? Okay? So now you have a positive number divided by 0. What does that mean? What is the value of a positive number divided by 0? Pick up your calculator. What is positive number divided by 0? Use your calculator. You get an error term. You get an error. Okay, there's something called the Hospital rule, where a positive number divided by 0 gives you positive infinity. If a negative number divided by 0 gives you negative infinity. So if it's positive infinity when stock price is greater than x, then at the limit, again, d1, d2 approach 1, and therefore nd1 and d2 approach 1. Right? Okay? So when nd1 approach 1, what happens to the value of your call? Again, you replace it with 1 and you get the value, right? So if you replace with 1, again s times 1, x times 1, you have this same thing here, right? But we said it's simply equals to s minus x. There's no more present value. Why is that so? Because time equals to 0, right? So this is another common error among students. Okay, you forgot that time is equals to 0 at expiration, and you continue to use s minus present value of x. Because it's easy to make that mistake, right? If this is 1 and this is 1, naturally you get back to this formula here, right? But you have to be conscious that t is equals to 0. Okay? So that's the effect of time. Now, what about bankruptcy? Any questions so far up to this stage? What is bankruptcy? What happens during bankruptcy? Okay, maybe one of you can. What about you? What happens to when a company goes bust? Stock becomes 0. And when stock becomes 0, what happens to D1 and D2? You want to help us? So stock price is 0 now, right? When the firm goes bust. So you raise S is 0, right? And what happens to your D1 and D2? Just like what we saw earlier on for on the slide for time, right? Because now you have s equals to 0, your s is the numerator, right? So 0 over a positive value, right? So what you get? Negative infinity, right? So with negative infinity, your d1, d2 approaches 0, right? So when it approaches 0, what does it mean? Well, again, you substitute it into this formula here, s times 0, x times 0, right? And therefore, what do you have? It's equals to 0, right? Now again, intuitively, so what we're saying is when the stock goes past, the value of the call is equals to 0, right? Now, I'll bring you back to 2 weeks ago. We talked about that too, right? What is the minimum value of a call? Right? And when does that happen? Right? So we talk about different scenarios when x is 0 or when s is 0, right? So now we look at it mathematically again. So no risk. Well, same thing. If no risk means sigma is equals to 0, right? So this becomes 0. So something divided by 0, if this, now remember this has to be positive, right? Okay? So if this is positive, then positive number divided by 0 again give you positive infinity. Now if this is if this is not a positive number, such that s is less than x, then it simply means that your call is out of the money, right? So now you have a negative number. So negative number divided by 0, negative infinity, your d1 approach 0 again, right? Okay? Is that clear? Okay, so we talked also that 2 weeks ago that what happens when x equals to 0, and we say that the call becomes a stop, right? Because the value of your call is s minus x. So if x is 0, then the call is equals to simply s, right? So we say it becomes a stop. But we didn't prove it, right? Mathematically, so this, again, is the proof, okay? The same thing, right? S over x. So if x is 0, it becomes positive infinity. So d1, d2 approach to 1 again, right? So if d1 and d2 approach to 1, this becomes s times 1, x times 0, but because x is 0, this thing is gone, right? So c becomes equals to s, okay? So if you are to ask to explain or prove that the value of a call is equal to that of a stock when the exercise price is equal to 0, this is how we're going to prove it. Okay?
Is that why the BlackScholes can't explain the dividends payments?
Oh, you can.
But if a call is
No,
like,
you can account for dividend payments, but you cannot account for early exercise.
yeah. But if that proves the call is equal to a stock pays dividend,
If it's equal to a stock, what?
the stock pays dividends, but the call, if you are holding a call, it's an exercise price of 0, you can't get the dividend payments.
Well, if its exercise price is equal to 0, why can't you get the dividend payment? If exercise price is 0, it simply means that you pay nothing and you get the stock, right? Because when you exercise the call, you pay out the exercise price, right? So if exercise price is equal to 0, you are paying nothing. You don't have to pay anything, you get the stock.
But
Right?
how do you receive the dividends payments?
So if you receive the stock, then you will receive the dividend. But again, a call is not the same as a stock, although when x is equal to 0, it's similar, which is why if you look at the formula here, s nd1 minus x, present value of x nd2, right? So if x is equal to 0, then this term goes away. So c becomes s times nd1, right? Now, we don't say that c is equal to s. It's equal to s times nd1. And because nd1 is a probability range from 0 to 1, so the value of a call can never be greater than the value of a stop, right? Mathematically, right? But again, intuitively, you know it's true too, because as we discussed 2 weeks ago, calls expires, right? Whereas stocks go on in perpetuity, right? So I hope you can see the linkage of all these things? You okay? Okay, what happens to zero interest rate? Well, with interest rate, I think that the more important issue here is not, well, again, calculation is quite simple, right? We've gone through almost every variable. With interest rate, what is more important is, okay, I'll just turn on all the slides first. Okay, with interest rates, what is more important is the implication. Now, you know many countries now have negative interest rates, right? What is the interest rate in China now? 2%. Sure. We said 2, we said 3, so that's arbitrage proportionality here. What is Australia? Okay, it's important to understand interest rates across countries. Okay, I will talk about that later on when we look at futures, because there's something called carry trades. Okay, so that interest rates has implications, and if you are trading foreign exchange, foreign currency, then it's even more important to understand that. So we talk about that in futures. Now, it is more important to understand the implication of interest rates because remember 2 weeks ago we said when we talk about whether or not we will exercise the call early, what are some of the reasons that we said that we won't? Did we say we exercise the call early if it doesn't pay a dividend? Would we exercise early? No, right? And what are the reasons that we won't exercise early? One of the reasons is related to interest rates. Do you remember? Yes, so what does that mean? So we talk about how calls save you money, right? Because by not exercising the call, you're holding on to the strike price, and therefore you can earn a return on the strike price. Now conversely, puts cost you money, right? Because by not exercising, you're not receiving the strike price, so you lose the opportunity to earn interest on the strike price, right? So if interest rate is negative, what do you expect the value of a call to be? Or if interest rate is going down, do you expect, what is the impact to the value of your call? Do you expect call to go up when interest rate is going down, or do you expect calls to go down? So if interest rates is going down, okay, do you expect the value of your call to go up or go down? Everything else remains the same. Go up. Who has a different answer? Interest rates is going down, and everything else remains the same, right? Do you expect the value of your call to go up or go down? Go down? Go up? Any different answer? How about people at the back? What do you think, sir? Right at the back.
I think if like the interest rate go down, so stock price maybe go up. So I think.
Cool. Everything remains the same. Okay? Strike price, volatility, everything is the same. Just the value of your call and interest rate. So if interest rate goes down, you would expect the value of your call to go up or go down. You have to be sure, and I think you know the answer. You're not sure because you didn't think through. Remember what I just said before I asked you this question? Calls save you money, right? So if calls save you money, it means the strike price that you're not paying out earns you an interest, right? Because you have it in the bank. So if interest rates goes down, is that good or bad for you? Good or bad? Bad, right? So if it's bad for you, what do you expect the value of the call to be? It must go down, right? You okay with that? Okay? So if you think through the process, you will always know the answer. Okay? You say you don't know because you don't think through the process. Okay? You will know. You try and link them all together, you will have the answer. Okay? Okay, we'll look at one final example before we go. So we saw how we could account for dividend in the binomial model. Can someone tell me very quickly how you account for dividend? How about you, ma'am? How do you account for dividend in a binomial model? No, how do you account for dividend? When I stop based on dividend, in calculating your option.
Discount the dividends payment back to time 0.
Right, why do you have to discount? Why can't you just take the dividend payment at the time that you pay the dividend? It's because then your binomial model becomes non-recombining, right? So in the same manner, when the stock pays a dividend, you need to adjust the price of the stock with the present value of the dividend. Okay, as we saw in binomial. So we're going to look at how to do it in the Black-Scholes. So stock is $8. Again, all of these are given to you. The stock pays a dividend of 10 cents, so ex-div in 5 days' time. Remember, with options, we're more concerned with cum-div and ex-div, right? When the dividend payment takes place, because whether we're holding a call or put, that helps us to determine when we're going to exercise the call or put, right? Still remember 2 weeks back? Okay? So, first you determine the amount of the dividend, which is 10 cents, and the present value of the dividend in 5 days' time is also roughly 10 cents, right? So subtract the present value of the dividend from the stock. So S, which is $8, minus present value of 10 cents, which is roughly 10 cents since it's only 5 days, you have $7.90. So remember, now you have to use the adjusted stock value. Okay? Another common mistake. Okay, use the adjusted stock value. It's no longer $8, it's now $7.90. So again, D1 is log S over X plus R plus sigma squared divided by 2 times time sigma square root time, right? So you get your D1, D2 is D1 minus sigma square root time. Look up ND1, ND2, put it into the formula, S ND1 minus present value of X ND2, okay? So again, I want to stress that calculation is all very simple, so long as you get the correct input, okay? You must know where to get the number. The mistake is always in putting in the wrong number. For example, using the stock price instead of the adjusted stock price. Okay? So sometimes students calculate the adjusted stock price and the stock pays a dividend. Now when you calculate the value of the option, they use the original stock price and not the adjusted stock price. Okay? So you have to be very careful with things like this. Yeah? Okay, so that's all for today.